Welcome to video number 9 in Advanced Fluid Mechanics. So we're going to be finishing off section 5 here, and I've shown what we're going to be covering in the white text here. We're also going to finish off the course, so this is the last video in the Advanced Fluid Mechanics course. And what we're going to do to wrap up section 5 here with boundary layers is to talk about some really important concepts that are associated with boundary layers, like flow separation. Then we're going to look at flow past a circular cylinder and talk about the von Karman Vortex street, flow past a sphere, and specifically looking at the dynamics of sports balls. And then we're also going to take a quick look at some perturbation techniques and then solve an example using a perturbation technique. Okay, so let's get started. Okay, so in section 5.7, we're going to look here at the effect of the pressure gradient. Now, so far, we've looked at boundary layers on flat plates. And so there, the pressure gradient of our external stream was 0, P di x equals 0. But if we consider that the surface of the body is curved, like in this figure here, I'll draw a streamline like far away from the body. That would be like up here. And then I'll trace over this streamline we're looking at right here to see what happens when the body's curved. Okay, so we go from a large area to a smaller area here, and then back to a larger area as the flow flows over this curved object, okay? So what happens is the streamlines converge towards the middle, right? Shown right here, into this smaller area. So to make sure that we have a mass balance, we know that the velocity has to increase. And to make sure we have an energy balance, and we know from Bernoulli, the pressure must go down. Velocity goes up, pressure goes down. Okay, but then we go from a small area to a larger area to the right of this object, and now we see that our streamlines diverge, right? And so for mass balance from a small area to a larger area, the flow slows down. So our velocity goes down, and that means our pressure goes up. Okay, so now we definitely do have a pressure gradient. So dp dx is less than 0 here, right? Because we go essentially from a larger pressure at the left, smaller pressure in the middle, and then our dp dx is greater than 0, right, as we move from the middle to the right, because we're going from a low pressure to a high pressure, okay? So what we're gonna do in this section is take a look at how this pressure gradient affects the shape of the boundary layer profile. Okay, so the boundary layer equation is given here. The pressure gradient, we remember, was found from the external velocity field to be this. Where x is the direction along the body, shown right there. Now at the wall, u is 0 and v is 0, so we don't have this term, we don't have this term. So we have this equation here. So in an accelerating stream, right, where dp by dx is less than 0, okay, this term also has to be less than 0, so we have that this is less than 0 when we're accelerating. I'm gonna erase this so we can see more clearly up here, shown in the figure there as well. Now the velocity profile, we know, has to blend in smoothly with the external profile at the edge of the boundary, right? So the slope, du dy, just below the edge of that boundary decreases with y from a positive value to 0, right? I'll show that really specifically. So it goes from being like a positive value to being like 0. That's how much u changes in the y direction, right? So we're seeing that. So at the boundary layer edge, second order differential is negative, right? Because the slope, du dy, went from positive to 0 as we increased in y direction. So the second order differential is negative at the boundary layer edge. And then our equation shows that it's negative, right? It's less than 0 at the wall as well. So presumably it's negative at the boundary layer edge, it's negative at the wall, so it's negative the whole way through the boundary layer, right? But when we look at our decelerating flow, so like from the middle to the right of this object, we have our dp dx greater than 0. Okay, so that means for this equation to work, this term also has to be greater than 0. Left-hand side has to equal right-hand side, right? So therefore, at the wall, we have a positive change in the second order differential, which means our slope must be increasing in the y direction. Our du dy is increasing in the y direction. But then we know it's negative at the boundary edge still, okay? So we have a change in sign of this second order differential where it equals 0. It goes from positive to negative, so at some point it has to be 0, right? This is a point of inflection, which is shown on our figure right here. In our limiting case of the flat plate, our inflection point was at the wall itself. Now the shape of the velocity profiles that we're showing in this figure suggests that a decelerating pressure gradient tends to increase the thickness of the boundary layer. We can also see this if we look at the continuity equation, which I've shown right here. So when compared to a flat plate, a decelerating external stream causes a larger negative du by dx term within the boundary layer because the deceleration of the outer flow will add to our viscous deceleration that's within the boundary layer. So therefore this will be larger, right? So therefore our V velocity, the velocity field in the y direction that's directed away from the surface, we see from the equation that'll also be larger for a decelerating flow. Okay, so the boundary layer thickens not only by viscous diffusion, but also by advection away from the surface, right? Because this V direction, velocity in the y direction, is normal to our surface. So we'll see therefore a rapid increase in the boundary layer thickness with X. Okay, now you may have seen some of this in an undergraduate level fluid mechanics. I covered this a little bit in my undergraduate fluid mechanics videos as well, so I'll put a link to those in the top right corner of this video. But just as a reminder, when our pressure gradient is less than 0, we refer to this as favorable. Okay, it's favorable because the flow likes that, right? Flows are driven from high pressures to low pressures, right? So this will actually help the flow, it'll increase the flow. That's why the velocity increases. When we have dp dx greater than 0, we say that that's an adverse, or other words that mean the same thing, like uphill, for example, pressure gradient. And that's because flows don't want to flow from a low pressure area to a high pressure area, right? So that's why we see deceleration when we have an adverse pressure gradient. Now, we'll see in the next section. So what happens is when you have rapid growth of the boundary layer in a decelerating stream, that can cause separation, where the external stream stops flowing in the direction parallel to the surface. Okay, and this is a really important phenomenon. So we're gonna look at that in the next section here. Okay, so 5.8 is about separation. So we've zoomed in here on our decelerating region in this figure here. And we just saw in the last section that the boundary layer in the decelerating stream has a point of inflection and it grows rapidly, okay? So this point of inflection implies that the fluid is slowing down in the region close to the wall. And we can see that because we have an adverse pressure gradient, right? That's pushing this way, okay? So we see in this velocity profile, we're slowest near the wall. Okay, so where these pressure forces are pushing against the flow, the slower velocities near the wall are going to be more susceptible to slowing down and ultimately stopping, okay, which is shown right here. And then as we continue, they can actually flow in the negative direction, right? As shown in this one right here, right? We have flow in the negative direction parallel to our surface. So if we have a strong enough adverse pressure gradient, we have this reverse flow, and at some point it's gonna meet the forward flow, okay? So what happens is if we have flow coming along this way and flow coming along this way, okay, we have this point where it's 0, and now because there's no velocity right here, as shown from our profile, we have fluid that wants to come in, right, from the left-hand side, and fluid that's flowing against it from the right, and it has nowhere to go. So because we have to have a mass balance, it has to go this way, right? And that's why we say it separates, okay? Because it moves away from the surface. So that S point there is marking our point of separation. So it's defined, right, as the boundary between the forward flow and the backward flow of the fluid near the wall where the stress vanishes. And so at the wall, right, we see that's the point where our du by dy at the wall equals 0. That's our separation point. The figure actually shows as well that at the point of separation, we have a streamline that intersects the wall at a definite angle. That's shown right here. Okay, now some flows are better able to withstand these adverse pressure gradients than others, okay? And it turns out it's really important whether or not the boundary layer is laminar or turbulent, okay? Also, the shape of the object matters a lot too. So if we have a very blunt body, so where there's a very steep change in this curvature, right? So you very quickly go from a small area to a large area, that leads to very quick separation. However, if you have a very gradual trailing surface of a thin body, sometimes you can overcome the weak pressure gradients that are involved in that. So one way to avoid separation is to have the trailing section of a submerged body gradually reduce in size, which gives it what we call a streamlined shape. Now we've seen from experimental evidence that the point of separation does not depend on the Reynolds number as long as the boundary layer is laminar. But if we have a transition to turbulence, that can actually dramatically delay the boundary layer separation. Okay, so we're saying a turbulent boundary layer is much more capable of withstanding an adverse pressure gradient. And this plot shows this really nicely. Okay, in our turbulent velocity profile shown here, we have much higher velocities, okay, closer to the wall, right? And the flow's more chaotic and there's more mixing, right? So it's able to transfer its momentum more easily. Whereas the laminar profile, which is this more parabolic one here, the velocities closer to the wall are lower. Okay, so it's not as able to withstand those adverse pressure gradients. We'll see in the following section on specific shapes sort of exactly where these separation points occur, because this is a really important phenomenon, especially for drag force. And what happens is after it separates, the pressure downstream of that tends to stay at what the value it was at where the separation occurred, so it stays fairly low, right? So this low pressure at the rear of these bodies tends to pull back against it, right? Like you could think of a vehicle that's trying to drive, so where the flow separates, right, you'd have a low pressure zone at the back, it would pull back against it. That drag force is also known as form drag. right? Or pressure drag. And again, I discussed this at the undergraduate level of fluid mechanics, which you may have seen. So we won't go into too much detail here. We'll focus on the new things for advanced fluid mechanics. And I have a link to the video where I talk about that in the top right-hand side of this video. Now we can also get separation in internal flows. It doesn't have to just be the external flows, where an external flow is a flow like around an object, right? And an internal flow would be a flow like inside a duct or a pipe, for example. So I'm showing that in this figure here, where this channel diverges abruptly. So we'd have like a favorable pressure gradient here, but an adverse pressure gradient right here, right? After the throat where the walls diverge. So we can have a large enough adverse pressure gradient that can cause separation as well, even in these internal flows. And that's shown like here and here, right? Close to the wall. So our boundary layer equations would then only be valid as far down as the point of separation. Beyond our separation point, what happens is the boundary layer becomes so thick that the basic underlying assumptions that we made to come up with our boundary layer equations are no longer valid. Also, we can only do numerical integration in the direction of advection, right? So along which information is propagated, but in a reversed flow region, that would actually be upstream. And so a forward, like downstream integration of the boundary layer wouldn't work after the separation point, right? Because we have flow in the opposing direction. And also one final problem is we can't apply our potential theory to find the pressure distribution in the separated region because our effective boundary of our irrotational flow, it's no longer just a solid surface, but it's some unknown shape that's encompassing like part of the body plus the separated zone itself. Okay, so we'd no longer be able to calculate the pressure distribution. All right, now we're going to talk about specifically flow over certain shapes. We're going to look at cylinders and spheres next. Okay, so let's look at flow past a circular cylinder now. So we talked previously about how we can get analytical solutions of viscous flows only in two limiting cases, when the Reynolds number is much less than 1 or a Reynolds number is much greater than 1. Because when the Reynolds number is much less than 1, the inertia forces are negligible over most of the flow field, and so we can get like a Stokes solution like we saw previously. When Reynolds number is very large, the viscous forces are negligible everywhere except close to the surface, and then what we do is we get a solution by having this irrotational outer flow with a boundary layer near the surface. Okay, in the intermediate ranges of Reynolds numbers, it's extremely difficult to find analytical solutions. Okay, so we have to rely on experimentation and numerical solutions. And so what we're going to do in this section is look at a range of Reynolds numbers over a circular cylinder as Reynolds goes from small to very high values. Okay, so we start with low Reynolds number flows. This is creeping flow around a cylinder where Reynolds is less than 1. And I'll just make a note here. Reynolds is U infinity d over nu for this discussion based on the upstream velocity and the cylinder diameter. Okay, so we have some vorticity that's generated close to the surface because of the no slip boundary condition. But we saw in the Stokes approximation, this vorticity is simply diffused, not advected, which results in fore and aft symmetry. And that's shown here in this figure. As Reynolds is increased beyond 1, the vorticity is increasingly confined behind the cylinder because of advection. So we observe two small attached or standing eddies, as we call them, behind the cylinder. So this is shown right here. Right? The wake is completely laminar and the vortices act like fluid dynamic rollers over which the mainstream flows. As Reynolds number is increased, these eddies get longer and longer. Okay, now we'll talk about the von Karman vortex street. As the Reynolds number increases beyond 40, we actually get an unstable wake behind the cylinder. So we end up with a slow oscillation where the velocity is periodic in time and downstream distance, with the amplitude of the oscillation increasing downstream. Okay, so this is shown in this one right here for this range of Reynolds numbers, and we can see it in the picture as well. So you end up with this interesting pattern here. So when von Karman investigated this phenomenon and showed these images, there's a similarity of this wake with footprints in a street. So that's why it's been named the von Karman vortex street. The vortices move downstream at a speed that's smaller than the upstream velocity u infinity. And so that means the vortex pattern slowly follows the cylinder if it's pulled through a stationary fluid. Okay, so in the range of roughly 40 to 80 Reynolds numbers, the vortex street doesn't interact with the pair of attached vortices, but as Reynolds is increased beyond 80, the vortex street forms closer to the cylinder, and the attached eddies, whose downstream length is now like roughly twice the diameter of the cylinder itself, because remember we said those will lengthen as Reynolds increases, they themselves begin to oscillate. And so these attached eddies will periodically break off alternately from the two sides of the cylinder. And so while the eddy on one side is shed, the one on the other side forms, resulting in an unsteady flow near the cylinder. And then as these vortices of opposite circulations are shed off alternately from the two sides, the circulation around the cylinder changes sign. So we we end up with an oscillating lift or lateral force of these cylinders. Okay, now if the frequency of that vortex shedding is close to the natural frequency of some mode of vibration of the cylinder body, then we can get very extreme lateral vibrations that have been observed in these cylinders. So the engineering of structures like suspension bridges or oil drilling platforms are designed so that they break up the coherent shedding of vortices from cylindrical structures. You can do this, for example, by including spiral blades that protrude out from the cylinder surface, and they'll break up the span-wise coherence of the vortex shedding, so forcing the vortices to detach at different times along the length of these structures. And that's shown like in examples right here, right, of these spiral blades. There's actually a professor at Ontario Tech University, Dr. Ataf Mohani, who studies this phenomenon in great detail. So there are other examples where this occurs, for example, in heat exchangers, where we have flow over cylindrical tubes. And so he and his research team have looked at a number of different ways to help tackle this vibration and noise issue. I'll show a few examples of that here. Now, the passage of regular vortices causes velocity measurements in the wake to have a dominant periodicity, okay? So the frequency, n, is expressed as a non-dimensional parameter that's known as the Struhal number, which I've shown here. And some experiments have shown that for a circular cylinder, the value of S remains close to 0.21 for a large range of Reynolds numbers. For small values of cylinder diameter and moderate values of U infinity, the resulting frequencies of the vortex shedding and oscillating lift lie in the acoustic range. Okay, so that's where we would experience this noise, right? For example, at U infinity equals 10 meters per second, a wire diameter of 2 millimeters, the frequency that corresponds to a Struhal number of 0.21 is n equals 1050 cycles per second. So the singing of telephone and transmission lines has been attributed to this phenomenon, right? Where you can hear a noise coming off these transmission lines when there's a certain wind speed, right? Now, below Reynolds number of about 200, the vortices in the wake are laminar, and they continue to be so for very large distances downstream. Above 200, the vortex street becomes unstable and irregular, and the flow within the vortices themselves becomes chaotic. However, the flow in the wake continues to have a strong frequency component, corresponding to a Struhal number of roughly S equals 0.21. And then above a very high Reynolds number, like 5,000, let's say, the periodicity in the wake becomes imperceptible, and the wake can be described at that point as completely turbulent. There's a lot of interesting examples of this, so I went into YouTube and searched for von Karman vortex street examples, and I found these interesting satellite images. I'll put a link to this video in the video description below. And so we can see this cloud structure over these mountain peaks can cause a vortex street amongst the clouds here, which is really fascinating. It's really stunning to look at. And a question you might be thinking of is, well, how is that actually a 2D problem? And what's interesting is in the atmosphere, you can get very stratified flows, right? Meaning they're very layered flows, okay? And that strong density stratification can prevent vertical motion. So you end up getting this 2D character that's necessary to get the formation of vortex streets exactly along the plane of like this cloud cover. Okay, now we're going to move on to high Reynolds numbers, and we'll do that on a new slide. Okay, so at high Reynolds numbers, the frictional effects upstream of separation are confined close to the surface of the cylinder, and the boundary layer approximation is valid as far downstream as the point of separation, as I mentioned previously. For Reynolds less than about 3 times 10 to the 5, the boundary layer remains laminar, even though the wake might be completely turbulent, okay? Now shown in the bottom part of this figure, if we look right here, for a laminar boundary layer, we get separation at approximately 82 degrees, right? Shown in the picture from our forward stagnation point. So you see the angle there. The pressure in the wake downstream of this separation point stays nearly the same, and it's lower than the upstream pressure, okay? So I'll show that here. So the point of stagnation would be right here, right? So that's our non-dimensional pressure, so P minus P infinity, divided by half rho U infinity squared. And then we've got the degrees, they increase, right, from 0 degrees. Our pressure here is decreasing, right? So that's a favorable pressure gradient, less than 0. Then the moment right here where it starts to increase, we end up with separation. So we said right at about 82 degrees, somewhere in this region right here, we get separation. And then what this plot is showing us, right, is like with very little change, we get basically the same pressure all the way along the back. And so after this point of separation, right, shown right here and here, all along the back surface here, we have this lower pressure, much lower than what was at the front of the sphere was up here. Right? Okay, so much higher pressure here, lower pressure here, so high P, low P, and that causes a substantial pressure drag, right? Where you get a lot of force pulling back against this circular cylinder. And so this is a plot here in the bottom right of our drag coefficient plotted against the Reynolds number. And so we can see in this zone right, where we're sort of like pressure dominant, we have a very consistent drag coefficient. CD is roughly about 1.2 in that range, okay, because the point of separation remains pretty much the same along this range. So our drag coefficient stays the same because we're really pressure drag dominant in this zone here. Now our critical Reynolds number, which is approximately 3 times 10 to the 5, remember, these things depend on a lot of different factors, but it's approximately 3 times 10 to the 5. And that's where the laminar boundary layer becomes unstable and has a transition to turbulence, okay? And now we mentioned a turbulent boundary layer can overcome a larger adverse pressure gradient, okay? So that'll push our separation point back further, right? Because they can fight back against this adverse pressure gradient much better than the laminar boundary layer can. So that's shown over here in this picture, where we're showing a separation point that has moved back to about 125 degrees. So all the way back here, right? Instead of 82 like in the laminar case. So we're gonna have a much thinner wake behind this cylinder, right? So this wake would have been like this large here. This one here is shown as being about this large here, right? So it's much smaller, so it's pulling back less against the cylinder, but also, time for a different color. If we're following this line here, right? You see we have favorable pressure gradient till we get to about 90 degrees. Okay, this is for a Reynolds shown as 7 times 10 to the 5, so above our critical point where it's turbulent. And then this flow is able to push back against this adverse pressure gradient. Still adverse, but the flow still keeps going. It doesn't separate till about this point right here. Okay, so now the pressure that's behind this cylinder is this one here, right? Which is much higher compared to the laminar pressure here. So it's still a lower pressure than the front of the cylinder, but not as low as the laminar one. So not only is the boundary layer thinner, but also the pressure's higher. So it doesn't pull back quite as much. So that's why when you have the separation point shown here, right, the drag coefficient dramatically drops, okay? Goes from about 1.2 to about 0.33 at the point of transition. And then we see, I'll erase this just so we see this clearly, this actually climbs back up a little bit. As the Reynolds number goes up, this drag goes back up. And so what happens is our separation point slowly moves upstream as the Reynolds number increases. Now the critical Reynolds number, where this boundary layer has this transition, is affected by 2 factors: the intensity of the fluctuations that exist in the approaching stream and the roughness of the surface, okay? An increase in either one of those decreases our Reynolds critical number. So that value of like 3 times 10 to the 5, that's valid for a smooth circular cylinder at low levels of fluctuation. And so that's why you get this interesting effect where you can actually reduce the drag on a cylinder by making it rougher, right? Because if you're pressure drag dominant and you can switch that boundary layer into a turbulent boundary layer, you'll get a much smaller wake, and so you have much less drag, right? So it's a little bit counterintuitive, right? You can roughen up the cylinder and actually reduce the drag that's experienced along the cylinder. That's pretty cool, right? Okay, now we're gonna look at flow past a sphere. Okay, so this plot here shows a drag coefficient for a smooth sphere. So we can see a similar behavior to what we saw for the circular cylinders in the previous section. So the circular cylinder, those results qualitatively apply to flows over a wide range of 2-dimensional blunt bodies. For example, you'll see a vortex street in flow perpendicular to a flat plate as well. But the flow over a 3-dimensional object is also very similar, but has one fundamental difference in that you don't see a regular vortex street being formed. Okay, for a flow around a sphere at low Reynolds numbers, there's actually an attached eddy in the form of a donut-shaped ring. And then this ring eddy will oscillate, and some of it breaks off periodically in the form of a distorted vortex for Reynolds numbers above 130. The behavior of boundary layer around a sphere is also really similar to a circular cylinder. In this plot, we see the transition to turbulence right here, which is roughly at Reynolds critical, approximately 5 times 10 to the 5. And so we see this very dramatic drop, right, in our drag coefficient that's plotted here. And then the separation, similar to the circular cylinder, separation point moves upstream. So from A to B there, we're getting an increase in the drag coefficient as the separation point moves upstream and makes the wake a little bit larger. We get an increase in our drag coefficient. We're also showing on this plot the Stokes flow, which is what we solved for before, creeping flow around a sphere. And so I included those equations here so we could see this was the drag right here. And then our CD, our dimensionless drag coefficient, we got that it was 24 over Reynolds. And that's what we're seeing with this dashed line right there on this plot. Okay, so now we can talk about one really cool example of this is the dynamics of sports balls. And this increase in drag from A to B actually becomes really important when we talk about the dynamics of sports balls. Okay, so let's start by looking at cricket balls. So I've shown a cricket ball here, and it has a prominent seam on it, roughly 1 millimeter high. And the orientation of this seam is responsible for bending the ball's path as it moves. So it's been known to bend when it's thrown at high speeds of around 30 meters per second, which as a reference point is about 108 kilometers per hour or about 67 miles per hour. And that gives us a Reynolds number of approximately 10 to the 5. Reynolds again is U infinity times the ball's diameter over nu. Okay, and you'll notice that this is a little bit less than the critical value of 5 times 10 to the 5 that would be necessary for the transition of our boundary layer on a smooth sphere into turbulence. However, the presence of this seam can cause the boundary layer to trip into turbulence on one side of the ball, but stay laminar on the other side of the ball. Okay, now because our turbulent boundary layer separates later, what can happen is, so in this picture right here, right, the flow that goes this way encounters the seam. Okay, so we get turbulent, right? Whereas the flow coming this side of the ball is smooth, and so that one stays laminar, okay? So from this point back, right, the laminar boundary layer will separate at about, let's say about 85 degrees, approximately. Whereas on this side, it can make it all the way from here to about 120 degrees. So then what happens is in this turbulent region, right near the 90-degree point, so we're showing it as A here, in the turbulent boundary layer, we get a much lower pressure. Similar to the plot we saw for the circular cylinder, right? The pressure drops much lower for the turbulent boundary layer around that 90-degree point, whereas the laminar, where it has separated already, this is at a higher pressure. And so the ball, right, we show our U infinity as if the ball is stationary, but the ball itself is actually moving this way through the air. And so because it has this force, this lower pressure on the left-hand side, right? So this is actually us looking downwards on the ball. So it's like we're above this ball looking downwards. So this ball will want to turn to the left, right? Because there's a lower pressure on the bottom side in this figure. So that'll make it turn left. And if the seam is angled on the other side, it'll turn to the right. And if it curves or swings out and away from the batter, that's known as an outswinger, whereas an inswinger swings in toward the batter and the wicket. Okay, now in the bottom right here, I've shown a smoke photograph of the flow over a cricket ball. Flows from left to right in this wind tunnel shot. The seam angle is actually 40 degrees, so a little bit more than shown in the other figure here. So you can see like the earlier separation on the laminar side, later separation on the turbulent side, that matches what we were just describing above. So that would have that downward force as well in the orientation of this picture. Now, when the ball is thrown, you're invariably going to get some spin that's imparted to the ball. Because the bowler holds it along the seam, you're generally going to get some backspin imparted along the seam itself. And this has the important effect of stabilizing the orientation of the ball and preventing it from wobbling too much. A typical cricket ball can generate side forces that are almost 40% of its weight, and a constant lateral force oriented in the same direction causes a deflection proportional to the square of time. So the ball travels in a parabolic path, and it can bend as much as 0.8 meters by the time it reaches the batsman. 0.8 meters, that's a lot. Now we know that if the ball is thrown too fast or too slow, that it doesn't bend. So what happens if it's too slow is even the seam won't trip that layer into turbulence, and so you won't have this imbalance in the pressure forces. And if you throw it too fast, you could be above the critical value, and so you could have turbulent boundary layer on both sides, which again would negate this effect of the pressure difference along the two sides. And now you can also see why a shiny ball is able to swing more, because the rough surface of an old ball can also cause the boundary layer to become turbulent on both sides. And so that's why cricket bowlers actually spend a lot of time polishing the ball and making sure it's really shiny right before they bowl. And so there you go. That's how boundary layers can influence cricket ball dynamics. Let's look at tennis ball next. Okay, now tennis ball is a little bit different. Tennis balls bend because of spin. So ball hit with topspin curves downward, and a ball hit with underspin travels in a much flatter trajectory. Okay, now this matches the Magnus effect, which is experienced by a circular cylinder, and that's accounted for by the Bernoulli equation. And I show that explanation of this in the undergraduate level fluid mechanics course. So again, there's a link to that at the top right corner of this video. But we think there's actually another influence on this ball that helps to explain something that we've observed that's sort of strange about this behavior. We've actually seen a negative Magnus effect at lower Reynolds numbers. Okay, so the forces that go in the opposite direction of that predicted by the Bernoulli equation. So I'll show that quickly here. Let's say you had a cylinder, right? Flow was coming this way, and it was moving with backspin, so this way and this way. What would happen there is as the flow moved along the top, the spin would make the velocity increase because it's in the same direction as flow. So that would make the pressure go down. Whereas on the bottom, right, that would cause the velocity to slow down, right, because it's against the spin direction there. And that lower velocity would cause a higher pressure, right? So the higher pressure on the bottom would cause a net lift of this cylinder for this backspin situation. Okay, so that's the Bernoulli explanation. We're going to look at another explanation that these spheres also experience while they're spinning, and this may be the dominant effect actually for spheres. Okay, so we're going to have to remember back to this plot here that I've shown where we have this critical point at about like 5 times 10 to the 5, where we get a dramatic decrease in the drag, but then from points A to B, the drag coefficient increases after the sudden drop because our separation point slowly moves back upstream. Okay, so let's first look at this sort of weird case of the negative Magnus effect, which frankly doesn't come into play that much because most of these balls move at a Reynolds number above the Reynolds critical point, and they're usually pretty rough, right? But anyways, let's look at the negative effect first in figure A here on the left. So we're showing spin in like the clockwise direction, right? So this way and this way. Okay, the flow's coming this way, so as it comes down here, right? On the lower side, the velocity relative to the surface is larger, okay? So that external airstream compared to the surface is larger. The Reynolds number's higher, so it'll transition to turbulence on the bottom here, right? Whereas on the top, the velocity now of the free stream compared to the surface, the relative velocity between the two is lower, so that will mean that it will stay at a lower Reynolds number, which keeps the boundary layer laminar. So same like the cricket ball, we get that delayed separation point here. So over here, we get a lower pressure, right? Before separation in the turbulent zone, it goes lower. But then on the top here, we had this separation point occur right here. So on the top, we have a higher pressure. So we would get like a downward force in this case going like this way, okay, which is our negative Magnus effect. So that's the opposite of what I just drew above for the cylinder that we've seen at these low Reynolds number speeds, which again, rarely happens, okay, in practice. But this case does show us that what's happening here is the opposite of what the Bernoulli effect would predict in terms of forces at these low Reynolds numbers. So that's what shows us that for these spheres, it's likely that these boundary layer effects that we're describing here are more dominant than the Bernoulli effects, which we saw in the cylinder. And so that's what we can learn from this low Reynolds number case, is about which of these explanations has the more dominant effect. Now in figure B, which is much more common at the higher speeds of tennis balls, and remember, tennis balls have a rough surface too, right? Like I've shown a tennis ball up here, and here's a close-up shot so we can see the roughness on the tennis ball. And so both sides of the ball will already have undergone transition to turbulence. So now again, we have the spin in the same direction, right? But we see a force in the opposite direction, okay? The force is shown upwards in this case, where we just saw it was downwards in A, right? So what's going on here? Well, both sides are turbulent now because our Reynolds number is above the critical value. Okay, so the relative velocity again on the bottom is higher between the free stream velocity and the surface of the ball, right? So this is a higher Reynolds number on the bottom, okay? Relative velocity, because the free stream is moving same direction as the ball's rotating, right? We'll get a lower Reynolds number at the top. Okay, now we're going to look at our plot over here in the top right. So the lower Reynolds number would be like closer to A, higher Reynolds number closer to B. Okay, so higher Reynolds number would have a higher drag coefficient, right? Lower Reynolds number would have a lower drag coefficient. And so this separation point on the bottom, right, with the higher CD at B, that's moved upstream, right? Whereas we have a further downstream on the top where the Reynolds number's lower, separation occurs further downstream, separation's further upstream on the bottom here. These are our like separation points. I'll just label that. Separation occurring earlier, therefore, is a higher pressure on the bottom. Delayed separation at the top, it's a lower pressure at the top. And so that higher pressure on the bottom, that's what causes this to have a force in the upwards direction, which is what we would experience in this case, right? Match the cylinder case that I drew earlier, right? So this would be like, because the free stream velocity is moving this way, right? So we can think of the ball as actually moving this way, right? And an upward lift force. So this would be our underspin, right? The ball's rotating this way, okay? And that's a force in the upwards direction that counters the weight of the ball, so it keeps it flying flatter for longer. Whereas the opposite case, if you had topspin, you'd actually have like the case of topspin, right? If the ball's going in this direction, would generate a downward force, and so that would cause the ball to drop more. You can also have a slice serve, right? So the rotation's on the side. Same idea if we were looking overhead then, and you sliced it on this like right-hand side here, the ball would like curve over to the like left-hand side over here, right? If we were looking overhead of like this picture here, you could get it to slice. And so that's the like really interesting way to explain the forces due to spin based on the behavior of the boundary layer, right? And again, people think this this effect may actually be more dominant than the Bernoulli effect that we commonly see to explain this behavior. Luckily, they both match. They're both in the right directions, so they both contribute to moving the ball in the same direction. But this is a really interesting way to think about it. Okay, now let's move on and look at baseball dynamics. Okay, now I'm really into the dynamics of baseball pitches. I love baseball. My son's a pitcher. And if you've watched my undergraduate videos, which again are linked in the top right corner here, you'll know that I love talking about baseball pitches. Okay, so I go into a lot of detail there where I talk about knuckleballs and curveballs. I'll just show you here, it's basically the exact same idea as we saw for tennis balls. So if we're looking from the side, let's say this is home plate here, right? And if the pitcher releases the ball, okay, and as a curveball, right? So curveball will spin top to bottom. It's like top spin when you release it. This is known as a 12-to-6 curveball. So, right, so it goes from top to bottom. What happens as the ball's moving this way, right? So we're getting air flowing over it this way. Okay, so relative to the ball's spin and the flow, we're getting a lower Reynolds number here, higher Reynolds number here. So our separation will be earlier here and later here. So where it's earlier, we have a higher pressure. Where the separation's later, we end up with a lower pressure, therefore higher pressure on the top. The force will be pushed downwards. Okay, so our curveball, which travels from our pitcher's hand, is gonna have a trajectory like this, and then it's gonna curve downwards. Okay, like that's our 12-to-6 curveball. Same idea we saw for the tennis ball. We also have some roughness, even though most of the baseball is fairly smooth, we have these stitches. And so when it's spinning quickly, it's sort of like there's a roughness across the surface of the ball. Knuckleball is released without spin. So what happens is it has kind of a similar effect of the cricket ball, where like wherever the stitches are, it'll trip to turbulence there at those roughness points. And so it'll cause higher and lower pressure zones that are sort of random and chaotic as the ball kind of slowly moves and doesn't have a real dominant spin, and that's why knuckleballs sort of move all over the place. Again, more detail on that in my undergrad videos. And we see in this picture here that I've shown, we have a smoke photograph here of the flow around a spinning baseball. So the flow is from left to right, right? So this way, ball is spinning counterclockwise, as in the example that I showed below. So that'd be like a curveball, we can think of it if we're looking at the side of the ball. And we see how earlier separation here, delayed separation here, right? So our wake moves upwards, right? And that accounts for this downward force that we're seeing, crowding of the streamlines too at our lower pressure we can observe. Now there's lots of different pitches as well. You can throw a slider where you, instead of having the spin come straight over the top, you tilt it to the side, right? And you release it from the side. So then you get not just the up down motion, but it moves from right to left or left to right as well, depending on if you're right or left-handed. Okay, so all sorts of really fascinating things going on there as well, which can be explained by understanding what happens with our boundary layers. Okay, now large Reynolds number flows with curved streamlines tend to generate additional velocity components because of the properties of the boundary layer, okay? These are known as secondary flows. A cool example of this is when you have finely crushed tea leaves in a cup of water, then you stir it really vigorously in a circular motion, and then once the motion stops, all the particles collect in a mound at the center of the cup, like as shown in this figure right here. We see them all piled up in the middle, and I'll show a video of this too. I found this on YouTube. It's a pretty cool video of this. Okay, so what happens is when we're stirring, right, we're imparting this velocity in the u theta direction. Okay, so we have this u theta as a function of r as we spin it, and that's large enough for the Reynolds number to be big enough that the boundary layers on the sidewalls and the bottom are really thin. Okay, so we spin it with this like u theta. It's a function of r. And then if we look at our r momentum equation, the biggest terms in the r momentum equation are these ones here. And away from the walls, the flow is inviscid, right? Okay, now the boundary layer on the bottom is thin. So our boundary layer theory says that di p di x equals 0 from our x momentum equation, okay? Thus, the pressure in the bottom boundary layer is the same as the inviscid flow just outside the boundary layer. However, within the boundary layer, u theta is less than the inviscid value at the edge, okay? So then the pressure, P as a function of R, is everywhere larger in the boundary layer than what's required for circular streamlines inside the boundary layer, so that pushes the streamlines inwards. So the pressure gradient within the boundary layer generates an inwardly directed UR velocity, right, towards the middle. And this motion is fed by downwardly directed flow in the sidewall boundary layer, right here, right? And then we have our UR velocity pushing towards the middle. We have our outwardly directed flow on the top surface, and it comes back up along the middle here. And so we can see this with the crushed tea leaves, right? They're slightly denser than water, so they descend by gravity or they're driven outwards by centrifugal acceleration. But if they enter this sidewall boundary, they're transported downwards and then to the center by the secondary flow. Okay, so if these tea particles enter the bottom boundary layer from above, they're quickly swept to the center and then drop down as the flow turns upwards. So that means all the particles will collect at the center of the bottom of the teacup. And again, sort of relating to our equation within the boundary layer, when we have this U theta velocity, we have positive di P di R. Pressure gets bigger as R gets bigger, so pressure's bigger towards the outer edge, smaller towards the inner edge, which drives the flow towards the middle, right? And so therefore this pressure gradient is driving flow towards the center, right? And that leads to this UR velocity, right, that we're seeing right here. The pressure gradient drives that flow towards the middle. And so there are practical applications of this as well. For example, the way sand and silt are moved around within rivers can be a function of these secondary flows as well. Okay, now we're gonna look at perturbation techniques. Okay, so we're gonna finish off section 5 by talking about perturbation techniques. Perturbation techniques are a really powerful tool that we can use to get approximate solutions to physical problems. Now, we're only gonna do a really simple description of perturbation techniques. I really just wanna make you familiar with the basics. If you wanted to go more deeply into this, it's a really specialized area. I recommend a book by Bender and Ortzag for that. But my goal here is to just make you aware that they exist so that if it ends up being useful to you, you can then pursue it more deeply. So the reason we talk about it in conjunction with boundary layers here is because, like, basically in boundary layers, we could reveal the physical basis of the boundary layer concept in high Reynolds number flow. And we saw when we scaled our equations, we had that 1 over Reynolds term, which was a small parameter. Okay, so we're gonna expand that here. So in any problem where we have a small parameter, okay, for example, like I'll just kind of sketch this out. So in high Reynolds number flows, for example, this small parameter, we'll call it epsilon, could be like the 1 over Reynolds, right? In low Reynolds number flows, epsilon can be the Reynolds number, right? Because that's our small parameter. For an airfoil, for example, this epsilon could be the ratio of the thickness to the chord length, because that'll be a small parameter. And what happens in these cases is the solutions can often be written in terms of a series that involves this small parameter, okay, where the higher order terms act as a perturbation on the lower order terms. And these methods are called perturbation techniques. Now, these perturbation expansions can break down in certain regions, specifically where you might have boundary layers. Then the boundary layers would be treated differently than the other regions by taking the lateral coordinate y and looking at it in terms of the boundary layer thickness delta, and then defining this eta parameter that is y over delta. Okay, and the objective is to rescale the variables so that they're all finite in this thin singular region. And I'm gonna go through a description here, and then following this, we're gonna look at an example of a regular perturbation problem so you can see this in action, and I think that'll help us understand it a little more, because it's a pretty unique way to solve these problems. So let's first talk about order symbols and gauge functions. So we'll have some complicated function, let's say f as a function of epsilon, and we wanna figure out how it varies as epsilon approaches 0. Okay, so these are our 3 options that I've listed here. So as epsilon goes to 0, we can have our function go to 0, right? So that would be called vanishing. We could have our function approach some finite value, right? In which case it's bounded. Or our function can go to infinity, in which case we would call that unbounded. But that still doesn't tell us a lot, right? Because it doesn't tell us how quickly the function goes to 0 or infinity as epsilon approaches 0. So what we'd have to do to get this behavior is compare the rate that the function goes to 0 or infinity with the rate at which certain familiar functions go to 0 or infinity, okay? And these familiar functions we used for comparison purposes, that's what we call a gauge function. The most common example of a sequence of gauge functions is 1, epsilon, epsilon squared, epsilon cubed. So just for a quick example here, so let's say we want to find out how our function sine epsilon goes to 0 as epsilon goes to 0. So we start with our Taylor series. I've got it written out right here. So then what we do down here, right, is we take sine epsilon divided by epsilon and then take the limit of that as epsilon approaches 0. And that gives us our comparison, right? So we see as we take our Taylor series and have the limit of epsilon goes to 0, we end up with 1. Okay, which tells us that sine epsilon tends to 0 the same rate that epsilon tends to 0, okay? Because we divided sine epsilon by epsilon and we got 1 as we took the limit of epsilon approaching 0. So they tend to 0 at the same rate. Another way we can express this is to say that sine epsilon is of order epsilon as epsilon approaches 0, which we write like this. right, with this O here. Sine epsilon equals O epsilon as epsilon approaches 0. A few other examples of this order down here. Cos epsilon is order 1 as epsilon approaches 0, and cos epsilon minus 1 is order epsilon squared as epsilon approaches 0, okay? And you could actually plug in the Taylor series for those and have a look at those yourself if you wanted to see in greater detail like exactly what we're talking about there. And then these are specific examples. We can generalize this, right? This order idea with the statement that I've written here. So our function f is a function of epsilon, right? It's considered to be of the order of a gauge function g, right? And written this way, right here, if when we divide f by g and take the limit as epsilon approaches 0, we get a where a is non-zero and finite. Now, sometimes we'll have cases where comparing to a familiar gauge function is unavailable or inconvenient. In this case, we can write it this way, okay, in the limit of epsilon approaches 0, if when we have our function and divide it by our gauge function, we take the limit as epsilon approaches 0, if that equals 0, okay? So that tells us that f is small compared to g as epsilon goes to 0, okay? So we use this O, and an example here is like the ln of epsilon is O1 over epsilon, okay? And the limit as epsilon approaches 0, and that's that like lowercase O we're showing right there. Okay, so that's sort of the basic idea here. Now we've familiarized ourselves with order symbols and gauge functions. Let's talk about asymptotic expansion. I'll do that on a new slide here. Okay, so an asymptotic expansion of a function in terms of a given set of gauge functions is really just a series representation with a finite number of terms. And so I've included the full description here. So let's say we had a sequence of gauge functions, g sub n as a function of epsilon, and then each one is smaller than the preceding one, right? So what that means is each term divided by its preceding term as epsilon approaches 0 would equal 0. Okay, that's what we mean by that. So then the asymptotic expansion of our function would be of this form here. We have these coefficients, and these coefficients, a sub n, are independent of epsilon. And then the remainder, or the error, is of the order of the first neglected term, right, which we're showing here. So we can also write this function of epsilon, where this curly sign means asymptotically equal to, and then we have our sequence of gauge functions with our coefficients. The most commonly used sequence of gauge functions is the power series, epsilon to the power n. And a good choice of gauge function will lead to good accuracy with only a few terms in the expansion. Sometimes the integral powers of epsilon don't work and you have to use other gauge functions. So again, there's like a systematic way of figuring out your sequence of gauge functions, but that you can refer to more detailed, more in-depth description of the analyses, like Bender and Norsag, for example. We're just going to do the basics here. Okay, now let's look at an example of this. I think it'll help to illustrate it a little more clearly. Okay, so we've got a simple example here of a perturbation expansion that's uniformly valid everywhere. So we're going to consider plane couette flow with a uniform suction across the flow, as shown in this figure here. So our upper plate is moving with the speed capital U, lower plate stationary, distance between the plates is d, and there's a uniform downward suction velocity, v prime s, through both of the surfaces, where the fluid comes in through the top plate and exits through the bottom plate. Now, to keep our notation more simple, we're going to show the dimensional variables with a prime and non-dimensional variables without primes. So just make sure you note that. Sometimes it's done the opposite of that, right? So our non-dimensional variables don't have the primes in this case, right? It's shown here, which makes it easier to write as we go through this analysis. And just note our coordinate system here too. So we can first simplify by saying that we have no change in the x direction for all of our variables. So we write the non-dimensional equations like this. So continuity there and x momentum right here. We have the following conditions listed here, which you're probably familiar with now. So we have that suction velocity, right, in the y direction. We have no slip at the bottom wall in the x direction. That one's stationary, so it's 0. And then no slip at the top wall again, so the fluid has to be moving the same speed that the solid surface is moving, which is capital U, right? So U is scaled to capital U, right? So that's why it's 1. Okay, we're showing exactly what the Reynolds is here and how we scale our y suction velocity there. So the continuity equation tells us that our y direction velocity does not change in y, okay? And therefore the whole way across it has to be this suction velocity, okay? The x momentum equation we can then simplify. I'll highlight that because we have this v term right here. Okay, so when we simplify that on this line, we can call that epsilon, and that's shown down here. That will be our vs times Reynolds number, or we can simplify further, and it's vs prime times d over nu. We'll assume the suction velocity is small so that our epsilon term is small. So this is what we talked about, right? We need our small parameter, right? So we say epsilon is much, much less than 1. And so basically what we need to do is solve this equation, right, with these boundary conditions. And just a note here, like, it is possible to get an exact solution in this case because of its simplicity, but we might not be able to get an exact solution in more complicated problems. So we're just gonna illustrate the perturbation approach here. And so what we're gonna do is we're gonna try to use integral powers of epsilon for our solution. So that's shown right up here. Okay, so let's say our velocity is this power series of epsilon. And what we're trying to do is find like these coefficients that we have here, u0, u1, etc. So then we take this, right, this form of our solution, we sub it in, right here, we sub it into these as well. And so we end up with this after we sub it all in. We sub into the boundary conditions and they become these ones right here. Now what we do is we find equations for the various orders by taking the limits of these equations here, these ones, as epsilon approaches 0. Then we divide by epsilon and we take the limit as epsilon approaches 0 again, and so on and so forth. This is equivalent to equating terms with like powers of epsilon. So up to order epsilon, this gives us the following sets here. Okay, so we first do epsilon 0. That gives us these equations here. Epsilon 1, that gives us these equations here. Okay, so now it's fairly straightforward to solve, right? So we take that 0 order problem and we get that our u naught equals y. Then we can substitute this into the first order problem, right? And we get this solution here for u1. So then if we stop there, the complete solution up to order epsilon is this expression right here. We see that this expansion has the second term is less than the first term for all values of y as epsilon approaches 0, right? So our expansion is therefore uniformly valid for all y, and our perturbation problem is regular. So this is plotted in our figure right here for epsilon much, much less than 1, right? This curve here. And it turns out that's actually a very good approximation because we can find the exact solution and compare it. We actually find that if we took our exact solution, expanded it into a power series of epsilon, the first few terms are actually identical to this expression that we got down here as our solution. Okay, so that's a really good approximation to our problem. So in cases, of course, where we can't get an exact solution, you could see that this is actually a really powerful method to solve these equations and get an approximate solution. Okay, so we're not gonna go into perturbation techniques any more deeply than that. Now you're aware they exist, you're familiar with some of the terms, you've seen how powerful they can be, and so there's a lot more to it than what I'm showing here, right? You can go very deeply down this rabbit hole. So with that, we're gonna finish off section 5, and we're at the end of the course as well. So just as a quick summary of this video, we finished off section 5, which is boundary layers and related topics. We talked about how for objects with curvature, we'll have a pressure gradient in our stream flow, and that can actually influence the boundary layer. We looked at how these adverse pressure gradients can lead to separation, which is a really important design consideration, especially because drag can be so dependent on separation. Then we talked about flow past a circular cylinder. We looked at the von Karman vortex street and different types of flow behavior you can expect based on a range of Reynolds numbers. We looked at flow past a sphere, also talked about the flow behavior there. We looked at a very interesting example of that, so the dynamics of sports balls, where it turns out the boundary layers are very important for describing how these balls behave, how they move, how we can make them move in very unique, and it ends up being very competitive for the sports you play to be able to control how these balls move, right? We talked about secondary flows that appear because of boundary layers. Then we looked fairly briefly at perturbation techniques, an overview of sort of the basic ideas, the basic terms, and then we did an example of a regular perturbation problem to sort of illustrate how powerful this method can be. All right, so that's all for section 5, and that's the end of the course here for advanced fluid mechanics. So that's all. Thanks for watching.